All right. Hi, everyone. Thank you for staying. It's like the last talk of the day, so it takes a lot of courage. Who here has used RPC, like explicitly, like RPC call? Who has used Erlang spawn and spawn a process to the remote node? It probably works fairly well for you guys. Things start to break when you ship a lot of data, and that's what I'm going to talk about today. I'm PJ. My actual name is really long, so you can call me PJ. I'm a distributed system architect at Splunk. Before Splunk, I used to work at Bugsense. We did a lot of Erlang there. We still do a lot of Erlang. Our infrastructure uses Erlang everywhere. And we're basically receiving 150,000 requests per second from mobile phones all over the world and process that data in real time. And shipping that data in between the nodes was a huge challenge for us. And you'll see why in a bit. This is the agenda. We're going to be talking about what happened, how we fixed it, what were the challenges. And then I'm going to show you a bit of Elixir Code and then a pretty good demo. It's incredibly over-engineered, but it's still fun. All right, so let's get into it. So the problem that we were dealing with was very straightforward. We have an infrastructure consisting of, well, right now it's more than 100 nodes that are receiving mobile analytics data. The web front end is receiving mobile analytics data. It's passing it to the backend. The backend is doing some processing and then disseminating that data, that basically JSON objects, to a bunch of different services. So there's incoming traffic that's getting amplified to the backend servers because one request from a single mobile device can go to a bunch of different services for different reasons. We used to use RPC call to ship the data between nodes. What made it interesting wasn't that we were just launching or just calling a process. We were literally shipping payloads like 10 kilobyte, 100 kilobyte, 2 megabyte worth of data between nodes. The traffic never stops. 24/7, 150,000 requests, 150,000 calls per node. The incoming requests are 150,000 requests coming in that get amplified, and we end up with as many, 150,000 calls per sec per node. So the problem that we used to deal with a year ago about when we developed GenRPC was that as soon as we turned the whole new system on, everything started crashing about, usually in the mornings, which was when the traffic from the phones was greater because everybody started using their apps. So the node started crashing, usually out of memory issues. Well, actually not usually, always out of memory issues. We started scaling up. After some point, nothing worked. After some point, we're like, okay, there's something going on here. We cannot like infinitely scale out, like launch more and more and more service. A, the money is going to run out, and B, this is not the way to solve a problem. There must be something breaking those systems. So we started digging around. And what we found is that the RPC library that you all know and love, what basically does is really a gen server call to a remote node on a named process in a remote node. And the named process is called Rex from remote execution. This is a single gen server that's running by default as part of the standard library, the standard distribution, on every Erlang node that you launch. And it's a single gen server. You really have to keep that in mind. It's a single gen server that's receiving messages from all over the clusters, all over the nodes in the cluster. So we started inspecting and tracing those mailboxes, and guess what? Those were the mailboxes we were looking for. Those were the mailboxes that were causing the out-of-memory issues and basically destroying our infrastructure. This is how Rex works. I'll go over it quickly. I'm presenting that to you so that you can compare it to the way GenRPC works. So a process will do RPC call. The RPC call will, first of all, initiate a distributed Erlang connection to the remote node through netkernel connect and the VM's internals. When it's connected and the state is established, it will serialize the RPC request, send it through the distribution port. That's very important. The distribution port is the port through Erlang exchanges, basically everything with every other Erlang node. There's a pair of ports for every node that's connected to every other node. There's actually a port to send and a port to receive. These are all mapped through EPMD. So it will send the data through the distribution port. While it's sending the data, this is incredibly important for you to understand right now, while it's sending the data, the port is blocked. It's physically blocked because it's actually sending data over the TCP channel. While this data is going through the channel, the VM cannot send anything else. I mean, it cannot multiplex like heartbeats or amnesia transactions with like whatever you're sending over the channel, that channel. On the other side, the node 2 will get the request, deserialize it, send it in Rex's mailbox. The Rex mailbox, this was the point of contention here. Rex mailbox, the Rex will pull the mailbox, process the request. Basically, it will spawn a process outside of the gen server because if what we're trying to call misbehaves, then it's going to crash the Rex server. So it just spawns a process, executes what we want. The worker process that Rex spawned will send the message back to Rex and say, hey, everything is done. Here's the message. OK, success. Rex will send it back over the distribution channel. Same thing happened here. The port is blocked while the data is transmitting back. Usually, the way back is not that big because you don't return huge binaries. You might return huge binaries. You're going to face the same problem there. The data goes back to node 1. The request is serialized, and the process that was calling the function gets the result. So we started doing experiments. We're like, OK, maybe RPC call is not appropriate. Maybe we should use cast because it's analytics data, and it's OK if we drop one. Don't do this at home, by the way. It's not advisable to be OK with dropping one. But we switched from RPC call to RPC cast. It improved the performance of the nodes that were sending data, but it didn't improve the performance of the node that were receiving data that were the ones that were having the problem, with a single mailbox and all. Also, cast is not stateful enough. If the node is down, if the node hasn't been connected, it doesn't care. It will just say true, everything is fine, and then you'll think that you sent the data, but you didn't actually. So we're like, OK, there's a single gen server. Maybe if we got rid of that. So what we did is we switched from RPC call to literally just spawning a remote process with our payload of data and then just waiting for a process to message us back like, OK, I've been spawned correctly. I'm going to process your data right now. It's not limited to a single mailbox. Problem solved, you would think. And we had to basically re-implement parts of the RPC call because remote spawn is stateless. You just get a PID. You don't get anything else. But then we hit this. This is actually not an error message. It's if you subscribe to system events with Erlang System Monitor, and you try to ship big binaries or like big data structures over remote spawn over RPC call over basically the distribution port, you might get this. This means that the distribution port is busy while you are sending data, and the Erlang VM tried to do something else, and it couldn't because the port was busy. We've actually found that through Wombat, the product that Erlang Solutions has built. Funny story, when we switched to remote spawn, the nodes were crashing for other reasons, but they were crashing much more frequently. They're actually crashing more often than the Chinese stock market. But what was happening was that because we were blocking the distribution port, Amnesia could not send the keep alive messages, the transactions, anything, to basically let the other nodes know that, hey, I'm alive, there's no net split, there's nothing going on. So the nodes were crashing for different reasons, but still crashing. The remote spawn architecture, I put that here in order for you to be able to compare with the previous solution. So the only thing that's different from here to versus RPC call is the fact that you don't do an RPC call to ship to a gen server. You directly use the distribution channel here to do the spawn, do the netkernel connect, serialize, send through the disk port, port is blocked while you're sending data, blah, 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 and then goes back. The response goes back explicitly from the process running on the node on the other side. This didn't scale because we're blocking the distribution port. So we needed to fix that. So we fixed the first problem. We removed the mailbox, the receiving mailbox. The second problem was much harder to fix because we had to basically invent a way of shipping data outside of the distribution port, out of band, as we call. And we did. We named the project GenRPC. And what it does, basically, it uses separate TCP connections, ergo separate mailboxes, for each direction that you're making, that you're sending data. So if I'm node A and you are node B, then I'm opening a TCP channel to send data over to you, and you will open a different TCP channel to send data to me. Those are two different mailboxes, one to send, one to receive, one to send from me to you, and one from you to me. That performs extremely well. It also, since it's using GenTCP and not the distribution port, it doesn't block the VM's distributed port. One of the latest features that have been implemented is using an explicit TCP listener to listen to requests about connections. I will get into that while I explain the architecture. But using a TCP listener, an explicit TCP listener, to listen for new connections, we basically got rid of the requirement of all the Erlang nodes existing in the same cluster, in the same subnet, or the same insecure network. Also, because of the way that the TCP connections are implemented, you can actually cast, send data, try to send data over asynchronously, and you will get some kind of connection state feedback, which remote spawn didn't offer. So the architecture, I'm so sorry about the size. This is the only way I could present it. I will try to walk you through. So as you do RPC call, you do GenRPC call. This will perform basically local named process lookup over a process named based on the node that you're trying to connect. So a GenRPC client that is trying to connect to node A will be named GenRPC client for node A. So we know exactly which process to look up. So it will look up the process. If the process doesn't exist, it will launch it. And the way that it launches it is it will perform a TCP exchange over a predefined port that's listening on the other side. I think it's 5369. I might be wrong. It was a random port that I just came up with. It will connect to that port and say, by serializing Erlang binary to term and term to binary, saying, OK, can you please, I'm client XYZ, can you please launch a Gen server that I can connect to and send data? So the TCP listener on the other side will launch a server. It will dynamically allocate a port through GenTCP listen 0. It will dynamically allocate the port, get that port, read that port from the server that is listening to that port, and report it back to the client and say, hi, I've launched a server. Here's the port that you're supposed to connect to. The client takes that information and explicitly connects to that port. After that, the connection is established, and then whenever you do GenRPC call, the GenRPC Gen server, the GenRPC client Gen server will get the messages, serialize them over, send them over the GenTCP port. The acceptor on the other side will get the message, deserialize it, spawn a process in the same way as RPC does. Spawn a process the results, send when the results are done, a message gets passed to the GenRPC acceptor. The acceptor will get the result, serialize it, send it over the channel, the TCP channel, to the client, and the client to the process that was calling it. That's more or less how it's structured. Some cool stuff. As I said, we name every process except for the spawn workers. Named processes help you understand, hey, I have this mailbox that's saturated. I don't know why. By doing process info and not even tracing, process info is much more lightweight on the person who is debugging right away, right there. What's going on? If you do process info, you can see that it's a GenRPC client, the GenRPC acceptor process that's being overloaded with messages. As I said, also unidirectional connections, which means I'm sending data to you through my own mailbox. If you want to send data to me, not reply, explicitly send data, initiate the connection, you open a different TCP channel. And the last feature that was implemented this week, using a TCP server instead of distributed Erlang allows communication over insecure channels. The previous implementation of gRPC 0.9, version 0.9, instead of having an explicit TCP server to basically listen for requests to launch servers, the client would basically do a RPC call, a bare RPC call to the node on the other side. They say, hey, can you please launch a server and just give him the port? And the other side will just launch it, and they reply through proper distributed Erlang channels. We got rid of that, so now you can use gRPC and send data over the internet. Well, not right now because it's clear text, it's not SSL-based. That's one of the future features we're trying to implement. But you don't have a two local Erlang nodes dependency anymore. Other goodies. We spawn processes, as I told you, the way that RPC does it. We spawn processes so that we don't ruin the acceptor service that's basically responsible for maintaining the TCP connection open. All the responses that gRPC returns are compatible with RPC, so appcast, true, which is incredibly inconsistent in the way that it returns. The response is sometimes it's true, sometimes it's okay, sometimes it's appcast. Yes, it's completely random. And we use a cool trick, undocumented feature called inet async. When you basically listen to a gNTCP socket, you can enable that feature, and you get messages whenever there's a connection. You don't have to block your server. You can wait for messages from the VM when a new connection is initiated. Performance-wise, our initial RPC, simple RPC implementation could handle about 50,000 calls per second per node until the mailboxes were saturated. Is not a problem of the performance of the rec server. Is a problem of the performance because of the huge payloads that we were sending. Even though there were binaries, the whole thing was much more heavy to the VM. Remote spawn increased the performance before Amnesia started freaking out and just crashing and destroying our clusters. RPC, gRPC currently handles about 150,000 calls per second per node without being maxed out. It's actually just handling these calls, all cool and breezy. Our nodes are 8-core nodes, and they're about 2. Their load is about 2.0, so it's ridiculous. But not everything is great. There are certain shortcomings. One is that there's a single client and acceptor mailbox. So instead of having a single mailbox for every node, we have a single mailbox per node. There's actually a feature, I'm going to talk about it later. There's a feature that I was inspired by the Erlang mailing list that we're going to implement. It's going to get rid of that limitation. Does not work with anonymous functions across nodes. That doesn't work anywhere, not even remote spawn, not even RPC, because mostly it's a VM limitation. When you declare an anonymous function and you serialize it to ship it over to the other node, it will ship the metadata. The definition, the actual function body will not be shipped. That's why it doesn't work. I don't know what kind of magic. Well, it's not magic. It's just probably just proper TCP IP handling of proper TCP IP handling. But distributed Erlang works better at detecting when nodes are down. gRPC is not quite there yet. We're basically leveraging all possible states that gTCP allows us to read, to react to like TCP error or TCP connection reset or all these situations, but sometimes there are no keep alives between the nodes, there are no explicit keep alives, so we could actually implement that, but there are currently no keep alives to probe the port to see if it's open. It will fail and you will get notified or you might not if there's a weird failure, but that's inherent to the implementation. That was good enough for us, and if you do use calls instead of casts, you'll be fine. And that's it. That's all the problems we found so far with using gRPC. Now to the Elixir part. When we wrote gRPC, I liked Elixir by reading some of the documentation. I had no idea how to write it. I assumed it was the same as Erlang. It actually is. but it's a lot more fun. So I wrote XRPC as an exercise for myself to learn Elixir, to learn the differences, the intricacies of the new language. The way that I implemented it and the way that I worked with Elixir was kind of different. So one takeaway is developing Elixir code is not the same as developing Erlang code. There are certain differences, but mostly if you've developed a lot of Erlang code, you'll be fine with developing Elixir code. If you started with Elixir code, my personal advice, my personal unsolicited advice is for you to learn how to code in Erlang first, and then when you go back to Elixir, everything will make more sense, because the syntax of the language and the semantics have been designed for that VM in mind. The features of XRPC used to be the same as GenRPC. They're not anymore because the project was a proof of concept, like, hey, I can build this in Elixir. GenRPC is more featureful right now in version 1. It's going to become much more, if you want to use it, don't use XRPC, use GenRPC. It works great, and it's much more performant than XRPC. Cool things I found while developing Elixir code. Elixir allows, and I love that, absolutely love that, Elixir allows more concise code. Instead of writing variable equals bad TCP, variable equals bad RPC, or variable equals error, you write variable in ABC, and then it's easier on the eye, it's more concise, and it's easier to reason about. You don't need to write boilerplate code for Gen Server and other Gen modules. Well, actually, Gen Server and Gen Event, Gen FSM, there's no proxy module in Elixir, so you actually have to write boilerplate code, but it's cool. I like the tools, I like Mix. I kind of like XUnit. It's not as advanced as Common Test, but it's getting there, and it's very easily programmable. You can instrument it very nicely to do what you want. Transparent interoperability with other Erlang projects that works out of the box. I love the fact that it forces you to write specs, it forces you to write documentation as part of your code, and writing documentation as part of your code actually makes sense, because then you can type H in your module and you can see the code that you've written. You get slave nodes. We actually use slave nodes in the XRPC tests to launch a remote node and send data and see what happens. And a feature that used to be true right now, it's not, up until version 0.9, you could use XRPC and GenRPC between Erlang and Elixir nodes through a clever use of basically the same module in Elixir. You could use it. We had like the supervision modules and the modules that were called by GenRPC. We had the same names in XRPC, so when you do an RPC call, you would find the same module, and vice versa. That doesn't really work anymore because we moved to the TCP listener architecture. There were some downsides. A lot of the things that Elixir offers are more powerful than the default Erlang ones. List comprehensions come to mind. They're much more powerful. They can cast your resulting list into a different object. They can do a lot of cool stuff. We got some performance. This is completely random to GenRPC. The next slide, I'm going to explain to you why I'm mentioning these performance issues. The biggest problem that I faced while using Elixir were that if you compile an Elixir project in a specific Erlang runtime system version, it will run only on that. And that's because Elixir does feature detection based on the runtime system that you run it in, and enables or disables features. That completely broke my Travis CI builds, because they build Elixir with Erlang 17, but you can choose Erlang 18 to run Elixir with, and you just all hell broke loose. So the Travis CI build of XRPC is broken, but if you actually run the test yourself, you'll be fine. The XUnit is not as powerful as Common Test yet, and Dialyzer, you actually have to add a plugin, which kind of sucks. I hope they integrate Dialyzer into Mix. A very interesting thing that I ran into while building Elixir code was that magic always comes with a price. So that's a completely pointless list comprehension in Erlang, and it takes about 1.5 seconds. But the same list comprehension in Elixir takes 3.5 times the time that it takes the Erlang implementation. If you use enum.map, which is basically a short circuit to list mapping, you get a comparable performance. This is not unexpected because, as I told you, list comprehensions in Elixir are much more powerful. But methinks there should be some engineering effort to short circuit for Erlang-based, Erlang idiomatic patterns of use for list comprehensions. This is all with theory. I have an incredibly over-engineered demo for you. Give me a second. So this is a terminal. I hope sufficiently big. Great. So I have 5 different tabs here. The first 4 tabs are 4 different containers running. XRPC, well, basically an Erlang shell. I'm going to show you basically the problem, how it manifests. I'm going to show you how XRPC interoperates with GenRPC, and I'm going to run a very fancy integration test using Docker in the last tab. So I have a GenRPC node here. And I'm going to try and ship. I'm going to try and ship data from one node to the other. So let me flush. All right. So, okay, we have connected nodes. I don't want to do that. Let's run it again. All right. So I'm going to read a huge file. And I'm going to try and ship it. I'm subscribing to the system events that I told you before. And I'm going to try and ship it to the other side, the tab next to it. So as you can see, I'm doing a remote spawn and just running a random function is binary for this huge binary that I'm sending. So now if I flush, I forgot to tell you, the VMs have been virtually slowed down through the traffic control tool on Linux to show you what happens with big packets and slow networks, or big packets and just normal performing networks, but they're just big. So I tried to ship this on the other side. We should be seeing this message. So this message basically is telling us that, hey, that thing that you did here is a very bad thing because the distribution port got busy, and I don't know, some things might break. Not the VM, because the VM considers whenever you ship data over the distribution channel, that works as a heartbeat as well. So the VM doesn't freak out. Amnesia would freak out though. There you go. All right. On the other side, basically, it's fine. Yeah, it's fine. So the message got delivered properly. Imagine this happening 1,000 times. You will have a VM constantly blocked with data, with shipping data, and Amnesia would freak out. Other applications that have heartbeats or any kind of synchronization would break. Let's see what would happen with GenRPC, though. That does the same thing. It will run this thing on the other side and just see what happens. It's spawning the client. It's trying to connect to the remote node. We're not getting any messages, so the VM is not blocked by it. So that concludes the first scenario. The second scenario would be for this node and this Elixir node to basically interoperate. So we can do a genRPC call to this, and it should return the other node on the other side, right? So these are all debug messages. It's basically telling you what's going on under hood, and we get the other node's name. And we can ship data over to Elixir in any way we want. On the other side, the Erlang node, the Elixir node, got the message. We can do the same thing and communicate back to the Erlang node. This is incredibly pointless. I just did it for a proof of concept. You should always use genRPC. I cannot stress this enough. It's under heavy development. XRPC is just a proof of concept. And then for the last demo, I'm going to launch how many nodes you want? A logical number between 1 and 10. 5. OK. So what this is going to do is it's going to launch 5 containers, instrument them to run genRPC in there, set the same cookie, run EPMD, and everything, and then it will run an integration suite that basically gets all these dynamic nodes that have been generated and just try and make calls to see how the tool performs. Now we're waiting. This is new because I actually published the project in Hex about 30 minutes ago. Oh, that's awesome. It failed. I think it's probably because I'm running other nodes on the other side. But actually, that's also a testament to how the integration test works. It tried, if we can check the tests, we'll see that it failed on a multi-call, which means multi-call, the way that we test multi-call is we don't use any node definition, so genRPC uses its internally defined nodes, which are different from the Erlang nodes, because genRPC has a node registry based on whichever node it has explicitly connected to, which is pretty awesome because when you join an Erlang cluster, you get a lot of crosstalk. Basically, if you join a node and you have this auto-connect, you join a huge cluster, so there's a lot of gossip. But with genRPC, you only connect to the nodes that you explicitly want, and that shows here too. I'm going to run this and show you exactly what I mean. So we have no nodes. Let's do a genRPC call on the other side. OK. So if you type nodes, no nodes. There's no distributed Erlang at work here. But if you write genRPC nodes, you'll see the node that you connected to. Incredibly handy. We use it on multi-call to do this thing. I have some time. There's the pointer. I have some time. I would like to show you some code, basically a side-by-side comparison of the genRPC code. The left side is genRPC, the right side is Elixir. You can see what I wanted to show you is basically the fact that while Erlang code is incredibly verbose, lines and lines. Actually, this is a God module. It has like all the functions, and we should break it down. Lines and lines of code. Elixir's code is much more concise. You startling, you have using defaults, you can define only one scenario of the functions that you want. You use the same semantics. You use where is. You can use everything you want. Specs are enforced. Docs are in place. And basically, you get the same amount of features in much less lines of code. And that's it. Enough with the demo. Sorry, where's the pointer? There it is. And I'm going to show you what the future holds, basically. And the future. The future are these 4 features. After that, I don't think there's any point in developing anything more. But we're planning on supporting SSL. because that makes sense if you want to ship data over the internet, including common name verification, so that if you connect to a remote node, the remote node will check your certificate and see if the node that you're connected from matches your certificate, the common name that is in your certificate. Great idea from the Erlang mailing list. Shard connections per node with a key, which you can use for consistent hashing, random load balancing, sequential load balancing, anything you want. We're planning on implementing just not only node separation, but also key and node separation. So it's going to make it much more performant for even more so higher workloads than what we're dealing with here. Blacklisting and whitelisting modules for RPC availability that goes hand in hand with the SSL module. If you want to expose your Erlang system to a service that consumes and produces Erlang messages, might not limit what you want to expose out of your applications to these interfaces. And get rid of GenTCP listen 0, mostly because if you want to actually use it through corporate firewalls and weird security scenarios, you actually have to have a predefined set of ports to use so that they can configure the firewall as well. That's it. Thank you so much. This is where you can find the packaging is in HexPM.
15 minutes for questions.
Okay, so go nuts. Please.
How do you do the naming since you're not using the Erlang distribution protocol? Naming those just by IP address? Or?
So when you use GenTCP Connect, you might we parse the atom that you used as a node. We split it. We only support long names. We split it on the @ symbol. We get the right side, and the right side, GenTCP supports both names, like domain names, like full FQDNs, and IPs. So that's what we do. We get that, and we connect to that, and we register based on what the client has defined. So if you define like RPC call node 1 and at 1, 2, 3, 4. This gets registered. I can actually show you if you want. We have enough time.
Does it interact with EPM to handle?
I'm sorry?
Does it interact with EPM?
No, not at all. Not in any way. That's deliberate. That's the point. We're trying not to interact with distributed Erlang. We used to. A lot of the interesting engineering stuff that went into GenRPC was that it was using a hybrid approach. Use RPC calls over the standard Erlang distribution to do lightweight operations like launch a listener, connect, like send supervision signals and stuff. And it was cool, but we found out that if we use a TCP server, we can get rid of the distributed Erlang, and this makes it more versatile for more peculiar scenarios where you have limitations like I cannot open up my firewall to a bunch of Erlang nodes talking to each other.
So it only allows one node per IP address?
Yes, that was one of the shortcomings. It only allows one node per IP address. We can actually, it's in the to-do. I'm not really sure. This can actually be fixed when you define a GenRPC connect or call or whatever you want. You can actually define a listener port. So you can have multiple nodes with different listener ports, and you can define that in your configuration. We can do that. It's straightforward. How many people here use multiple Erlang nodes in the same IP address? That's fair. If you're going to do a remote console and you don't start GenRPC in that node, I don't see the point of not being supported. The problem with not having multiple nodes is basically on the listener port. You'll have a E address already used, connection used, or whatever. So that's why it's not supported. But other than that, you can launch diagnostic nodes into whatever you want. Give me a second. I want to show you. So. Oh, I think it's because of the container. It's running in the container. Give me a second. That's a Rebirth 3 bug, by the way. Okay, so I'm going to cheat, and I'm going to call myself. That actually works fine. Half of the tests run like this. All right? All right. So you can see the processes are named here. I'm sorry, I cannot zoom. GenRPC. I'm sorry. There it is. So GenRPC acceptor 1 localhost 127.0.0.1 and the port GenRPC client. So there is a slight deliberate inconsistency in the way that we name the processes. The client gets named with GenRPC client and then the node name. But the acceptor and the server, they don't, because we don't have the node name on the other side. We only have the port that was allocated. And it's kind of pointless, to be honest. We can actually change that. I don't see the reason right now, but it cannot actually be changed. We can ship the node name here so this can have proper naming. For now, it's just named so that you know that this process is, this application has this process that's getting overwhelmed with messages, and that's the reason we name the processes. There's a proper supervision tree and everything, as you can see here. Other questions? Sure. Go ahead.
Do you notice if you're using GenRPC for a large payload, you're still going to have the same network connection, so your disk messages over the typical distribution port get slowed down?
No.
Does that ever get slowed down enough to cause timeouts?
No. There is, unless your server is actually overloaded and dying, which you actually have, then there you have workload problems. Unless your node is dying, the GenTCP port is completely decoupled from the distribution port, and if there's any slowdown in any of those two, it will be on the other port as well because of the general workload failure to schedule it properly. So no, we don't have any. This actually solved our scalability issues. This has been used in production for a year. No problems at all. No random disconnections. No full mailboxes. Excellent performance. It's going to get better because of some optimizations we did in process handling. But other than that, it's working great. Question, please.
Yeah. So you showed like the Elixir Code being significantly smaller than the Erlang. So do you use macros or
No. That was the point of developing the project, was to see, with no Elixir magic tricks, I think the only different thing that I used was the fact that the workers on the receiving side, on the server side, that are being launched to execute the RPC calls that you're doing are being supervised. So I'm using a task supervisor to launch a bunch of supervised processes that are simple one-for-one, and they just die when they complete the work. But it was very, very straightforward to implement, so I used that. On the GenRPC code, I just Erlang spawn, which is neither here nor there. It would be better if I had like a supervisor that would supervise these processes, but for simplicity, I just didn't go this way. It can be retrofitted. Please.
Is there a function definition files that client and server agree from that function?
I'm sorry, can you repeat the question? There was the clapping.
So is there something like a function definition file so that the client and the server agree the same signature of the same function that will be calling through RPC?
So the question is, if there are function definition files on the client and the server that basically serve as a contract, right? Like what you can call and what you can't. No, this is right now deliberate. It's how RPC works. You don't predefine what your whitelist or your blacklist, but we are planning on implementing that so that you can have, the server can have like a prop list or a hash or a dict with the functions, with actually the modules. Exposing functions and modules as well is too much granularity, in my opinion. Exposing, like saying, these are the whitelisted modules that I allow GenRPC to execute should be enough. And we're planning on implementing that, yes.
In any case, you can add another module with just the function that you want and call the other. If you want to reduce some particular one.
Yeah.
In the single one, the whole list module, if you want just two functions, you create your list with those two functions.
Exactly. You create an RPC. Usually what we have, and this is actually in production, the way we've implemented it is we have an RPC module for every application that we have. called XYZ_RPC, and we use that to interface with the system. That's just best practice. Questions? Other questions? Please.
So to jump over 19 fascinating engineering questions to the dumb question. Did you look at the bytecode or the EAF for the less performant Elixir list comprehension?
I actually tried looking into what made it tick. There's a lot of hardcore macro expansion, parse, transform, core Erlang work there. I kind of gave up after a while. I realized that it's expected because the list comprehension in Elixir is much more powerful and is implemented differently than core, than inside the Erlang language. So no, but it was very interesting to me. I realized that while researching Elixir Code, I was like, why this is happening? It's justified, but it's also surprising to see that a very standard language construct, not a library, not a function, not a module, but a language construct in Erlang, it performs different than the almost equivalent language construct in Elixir.
Essentially identical.
Yeah. So what's interesting, what's interesting to me is that, wait, there it is. So this is the RPC. This is the RPC module from OTP, from the latest OTP release, and you can see that this struck me as very, very interesting. All the meat of the RPC call function that you do is this. It does a named call to the Rex process on the remote node. So it actually is using by default distribution channels. It was very interesting to me. You kind of think that the VM does some things differently, but it's not alien technology. Most of the times it just uses standard things, and that's what you're supposed to use too, right? Yeah. Dogfooding your own VM code. Other questions? No? Thank you. Thank you so much for staying.